Okay, so in the last lecture, I promised some example of using one-complex theorem. So we'll consider the following case. So X will be an oriented genus G Riemann surface. Well, let's assume that this is greater than 0. Sphere is a bit special in some sense. So you probably already know from homework or even before that, this can be represented by a quotient over 4G gone by a certain equivalence relation. Namely, it can be realized as follows. So I have 4G edges, so I label this edge by, say, A1, and choose some particular direction. I label this edge by B1, and this next by A1, but I choose an opposite direction. Here, take B1 in an opposite direction, then I repeat the same thing for A2 and B2. So on, and I start with a closed 4G gone like this, and so what I do is view pairwise edges labeling by having the same labels, so that the points. My equivalence relation is a pairwise identification of points in this pair of intervals, so that which respects the orientations. So this point somewhere here is identified as here, and points are going in this direction and going in this direction. And of course, all points, it follows that all vertices here are built to the same point. They're all in the same equivalence class. Equivalence class is very good. Okay, so how can we use? So the idea is usually the general idea of using one-complex theorem is to cover my space. I want to play some fundamental group. I want to cover some space and some simple spaces, simple open subspaces, so that for each of them, it's easy to play fundamental. And so in this case, one way to do this is let me fix some point, some generic point at 0 in X. So to represent some point, some generic point inside this polygon. And what I want to do, so I can cover the whole X just by 2 subspaces, such that, so if this was the first, I just take a complement of my point. I just cut out this. So this is already something know about. And A2, let me take it to be a small open disk centered at X0. So it satisfies all the conditions of the theorem. So now here we have just a couple of spaces, so we don't care about triple intersections, but all of them are path connected, and the intersection is a path connect. So intersection is a punctual disk. This is same as A2 minus a point. It's path connect. So we can use one compact theorem. So in order to do this, we need to calculate fundamental groups of these three guys. So first, we know that so from one of the homework exercises, so we know that this is deformation retracts. This can be if I take out a point here, I can deformation retract it my polygon to its boundary, and the boundary, when I impose this equivalence relation, the boundary will be just after quotient over equivalence relation, the boundary will be just H sum of 2G copies of S1s, which I can, to be more precise here, if I, so these S1s, they are identified with the edges here, like this. Okay, and so we know that phi1. So at the end of the last lecture, we learned how to calculate the fundamental groups of wedge sums, if you know fundamental groups of each component as a sum. So in particular, this will be so we use the one competence theorem here for this particular case. So, so we know that. So there was a condition that this is equal to the free product of the corresponding fundamental groups under the condition that. So suppose I fix. Sorry, I don't write explicitly my base point here, but let me take here. Let me take a base point to be here. And so the condition was that for each S1, when I glue S1 for each S1, the condition was there was exist a neighborhood of my base point, which deformation retards to this point. For S1, it's of course the case, because I can always deformation retard this pair of intervals connected to intersecting at the point to this point itself. So I can use this property, and so how do I understand this group more geometrically? So this is so each of these is just Z, and we know that for each circle the corresponding generator corresponds to a loop which goes once around the circle. So the whole thing can be understood following. So this is a free group. Free group generated by alpha I, beta I goes from 1 to G, my genus, and okay, but where so So these elements of the fundamental group, they can be the classes of loops winding once around AI, BI, respectively.
For example, if we take genus 1, the torus,
Yes.
then we get is the free product of Z with Z.
Yes.
Right? But from the other hand, we know that it is Z times Z because T1 is just S1 times S1. So they are isomorphic in that case?
No. This is a fundamental group of X minus a point. So this is X, we are just, so far we are compressing fundamental group of this, of
okay,
A1.
not the Riemann.
We will see if for the whole space we will get an agreement with another calculation.
Okay.
We'll see. This is a fundamental group of A1, not the whole X. So if you want more you're more accustomed to this picture of the Riemann surface, for example. This is the case G equals 2, so you can this is G equals to like this. Okay, I will. So if you cut it, well, I'm not going to go into detail, but roughly these cycles will correspond to something like this. So you can write, alpha 1, beta 1. Well, what I'm writing, these are the cycles representing the corresponding generators in the fundamental. Yeah, but it's easier to imagine. To work with this picture for us. And okay, so now, so what about the fundamental group of this guy? Well, this is a disk, and so we know this is just a trio. This is a deformation retracts to a point. So the fundamental group is trio, and the third ingredient in the one-compass theorem is the fundamental group of the intersection. So we know that this is a deformation retracts to S1. So it is a disk, punctured disk. So I can take any. So suppose I fix some point x1 here, and this will be. So I'm calculating the fundamental group of x with the base point being x1. So in particular, I can deformation retract this disk, punctured disk, to a circle centered at x0 and passing through this point x1. So point x1, which belongs both to A2 and A1. So this one. And so this is. Let me write. Z, and I can assume this is so this is generated by a loop going once around S1. This. So let me choose this direction. Okay. So now we are ready to use one-compass theorem. this. So I pick some base points. I want to pick a base point which belongs to all of the A's, open subsets. So the general formula in this case, when they're just two covering subspaces, become the following. And so this is a quotient over normal subgroup generated. So there was the subgroup generated by let's say gamma. By all elements of this form, where gamma belongs to y1 of the intersection. Okay, so this guy is this thing. So when I do, so here I need to be more careful. So when I do deformation retract, I can always choose it such that x1 is mapped to this point here. I can always choose deformation retract like this. This will be an image of my base point. And there's a free group, these two G generators. So this is trivial. So this free product does nothing actually. And so here, so this is a free group with a single generator. So it's enough to quotient over to just a quotient of a subgroup generated by the sink when gamma is omega. And okay, so now I need to, so what is the image, so what is the J12 of omega? So J12 was a push forward of the inclusion map from so okay, let me remind you. So J12 was a push forward of I12, where I12 was the inclusion A1 intersection A2 to A1. Right. And the other way around for J21, if I just change here A1 to 2. So I need to understand where this, so the class, so I start with the loop here. If I step omega is a loop just going once around this one, and I want to understand what is image of its class in the fundamental group of A1, which we deformation retracted to this wedge sum of circles. So it's easy. When we do the deformation retract, this loop omega retracts the image of this loop omega becomes the loop which goes once around the boundary of our polygon. So but we can just track. So this is so from this we can easily read off what element in this group it corresponds to. So first, so it corresponds to the following. So it can be understood as a combination of loops going once around this this circle, so out one, and then going once around this B1 circle, B1. Then it goes once around this guy, but in opposite direction, because it's goes in opposite direction here. One reverse, and I continue in this way. Till beta G inverse. Now what about J21 omega? Well, we know that so J21 is supposed to be a map image of omega inside the fundamental group of A2, but fundamental group of A2 is stereo, so the image is also automatically one. So we end up of this thing being a quotient over a subgroup here generated by elements generated by a single element like this. So this is essentially the answer, but when I write it like this, it's a group given by the following generators. I mean, as you're probably familiar, we can specify groups by some generators and relations. So it's a group. The result is a group with 2G generators and a single relation is false. So this relation well, I can write it more completely like this. Is like an ordered product from I equals 1 to G. So I order it's going order in this way. For I inverse. So this is just this thing. Definition. So usually in the group, this is a okay. This is not well. This is a commutator of alpha I, beta I. Inverse. Of course, I can take inverse of the whole thing, because the condition is equal, with relation is equal 1, I can take inverse of the whole thing and just get a product of commutators equals 1. So this is the result for general G. The result is again a group with 2G generators and a single relation that the product of commutators the product of commutators is equal to 1. So let's see if it's indeed consistent with the case G equals 1, which we calculated in a different way. So G equals 1, X is homomorphic to T2. And so this calculation gives us a group with 2 generators and a single condition that we like this. And this is a condition that these generators commute. Well, this is just a product of the direct product of 3 groups generated by alpha and beta. And this is correct. So this agrees with the other calculation this is a fundamental group of S1 times S1, and therefore it should be the product of fundamental groups of S1s.
And the general one is not some particular.
No, for higher genus you don't have some simplification. This is more or less the simplest I think you can write. But you see, again, it happens like if you puncture at one point, it simplifies drastically. So it just becomes a free group. Any other questions?
When you say group generated by those elements, is it the free group generated by those elements?
Well, this is a free group. And this is you have generators and relations. This is not a free group. Well, this group, I mean, you can always write, I mean, one way to specify a group is to specify generators and all sets of relations. And the group is, I mean, the elements of the group are words up to equivalence relations that you can, the equivalence relations are such that you can go from one word to another word using these relations and group axioms. Any other questions? So in the next homework there will be, well, in this week homeworks there are more examples of fundamental. And I mean, of course, in the exam there will be at least one of the questions in the exam will be calculated using one compass theorem to calculate fundamental group of some topological space. But this is, I mean, this example of the genus G demonstrates a very classical example. And it's, I mean, this fundamental group appears in many other places. Okay, now we want to, so there is a kind of a nice relation between when we study covering spaces, there appears a nice interplay between the fundamental groups of the covering space and fundamental group of the space which it covers. And so in the next this lecture and in the next couple of lectures, including this one, we will consider some properties, some first properties of covering spaces. So we already already showed the uniqueness property of lifting a path. So I remind you the covering was specified as a map x tilde x, which satisfies certain conditions. And so before we considered a property, there was a property of uniqueness of lift of a path in X to a path in X tilde if we fix a starting point, and also lifting a path homotopy here to a path homotopy here if we fix the path in the beginning of my family. Okay, this is just a quick reminder. so first we want to show the following proposition. So let x tilde be a covering of x and P, so we have map P from x tilde to x, and let me fix, so I want to fix some base point x0 in x, and I want to fix its lift x0 tilde. It's fixed. Then following two statements are true. So it's a push forward of the covering map. It's a map of the push forward. It's a homomorphism from the fundamental group of x tilde to the fundamental group of x is injective. And second property is the following. The image of the push forward is the following subgroup here. So this is a subgroup. So yeah, the subset is a. So elements here are path homotopy classes of loops in X that start and end at x0. So all any element here can be represented like this, but the fact it belongs to the statement that it belongs to the image of P star if it satisfies the following condition, that it's so as you remember we denoted its lift by the lift of a polygon f tilde. So one of the conditions there were, so f tilde denotes is a unique lift which we know it exists and it's unique. From the previous, from one of the previous propositions, the lift of f to a plus starting at 0. So the condition here, the real condition here is that it also ends at x0. So in general, if we start with some path here f at 0, it may happen that, as you saw, it may happen that in general, it's lift. If you assume that it starts at x0 tilde, it doesn't end at x0 tilde. But there are some passes here, some loops here, which lift to loops here, loops in the cover that end at the same point as the stop. So the proof is rather simple. So what about, consider the first part first. So let me take some paths in the cover, and so we'll assume that it's a. Let me take a loop based at x0 in the cover, and so it's a by definition, it provides a lift of f, of a path f, which is a composition of f tilde. This is my projection map P. So I want to check this is injective. So I take some element here. So any element here can be represented by a class of loop f tilde like this, and assume that so I want to check that the kernel is trivial essentially. So I want to check. So let me take an element here, which is in the kernel. So it satisfies this condition. So what we want to show is that it implies that the class of f tilde itself is trivial. So how do we do this? So by definition of the push forward, so this equality means the following: that the the p star of f tilde is a class of f in the here, and the fact that this is 0 means that this is homotopic to the constant map starting at x0. Okay, so suppose denote the corresponding path homotopy by f, and so we know there is there exists a unique lifted by the previous proposition. There exists a unique lifted path homotopy f tilde. Should be path homotopy from the lift of f, which is f tilde, and a lift of this guy. But the lift of this guy is so the lift of the constant path is of course a constant path. And so this the lift of the constant path is a constant path, which is a loop starting and ending at x0, and this should become a path homotopic to f tilde. But this means that f tilde, this essentially means that the class of f tilde itself is trivial. It's a class in this pipeline. This means that indeed pi star is injective. The second part. So we need to provide some description of elements in the image of P star. So suppose the class of G. Suppose we take some element in pi1 of x, which is represented by some loop G, which is in the image of P star. So it's equal to P star of a class of f tilde for some loop in x tilde. It starts and ends at x0 tilde. So what does this mean? This means, so by definition of this class, this means that G is homotopic to, so this is the P star of f tilde is a class of composition of P and f tilde. So this equality just means that the G is path homotopic to this composition for some, let's say, path homotopy G. And again, let me denote this composition by F. So of course, F tilde provides the lift of F by definition. And so consider G tilde to be a lift of G. So we know, again, using, so we know that there exists we can uniquely lift path homotopy in this case. So we want to lift, we want to take a, we want to use the same, there's a unique lift of path homotopy G. This means that, so G is lifted by G tilde, and this guy is lifted by F tilde. So there is a path homotopy which lifts G between those two guys. And again, since this is a path homotopy, this means that the endpoints of those two paths should be the same. But so we know that the endpoints of F tilde are both x0 tilde. So this means that also G starts and ends at the same endpoint. Okay, and so we showed indeed that any element in the image is a class of G such that its loop it's lifted to a loop based at x0 tilde. So the summary is that so if the elements, so for generic loop here, it's lifted to some path which is not necessarily a loop, but the elements the elements in the fundamental group of X, which are in the image of P star, in one-to-one corresponds with classes of loops in X, which are also lifted to loops in X tilde. Questions? Before formulating the next proposition, we'll make the following remark. Well, it can be understood as a definition, partly. So remember that in the definition of the covering space, there was a notion of evenly covered neighborhood U of X, at some point X, inside the big space X, so there was open subspaces U alphas in X tilde, which entered in the decomposition, the disjoint union decomposition of P minus of U, And so we want to say that these U alphas are called sheets. Or we could say this sheets over U. So why is that? Because you can, as before, you can imagine picture something like this. So you have X, U, and it is covered by a bunch of by the joint union of open subspaces U alphas in X tilde, so that each of them is homomorphic to U, and P provides this homomorphism. So this is and it's not just a definition of what we call a sheet. And now the following statement is, kind of intuitively obvious, but still not quite completely trivial. So if X is connected, so let me denote, so suppose this subset where alpha runs over is denoted by I is connected, the cardinality of I, which of course can be also by the properties of the decomposition, it's of course the same the cardinality as the I. This I can be identified with the preimage of my point X here, because for each preimage, so each sheet here contains a unique element from this preimage. So the same as the cardinality of I, or equivalently cardinality of a preimage of X, is constant, meaning it's independent on the choice of X or this U. So how do we, this means again the number, so this cardinality might be called a number of sheets. This number might be not finite, so we have to talk about cardinal numbers. So intuitively it's kind of almost obvious, or if you wire, this should be, if X is continuous, and go to another point, this number, so locally X looks like a product of U and the discrete set I. And of course, they should be consistent everywhere. But so how can we actually prove this more formally? So one way to do this is the following. So let's consider a pair of points in X, and let me define the following equivalence relation. The 2 points in X are declared to be equivalent if and only if the cardinality of their preimages are the same. So again, if you talk about finite sets, this is just numbers. But for infinite, more precisely, we have to say there is a bijection. I mean, this quality just by definition means that there is a bijection. There is a bijection from this to this. Okay. Then note that we can know that the equivalence classes are open subsets in X. Why is that? So this follows from the following. So if I take some X in big X, there exists an open, evenly covered neighborhood containing point X. But this means that for any X prime, if I take any other point in this neighborhood, we necessarily should have that X tilde is equivalent to X, because these preimages, there's a bijection between these preimages, because both for any point, so if I take this decomposition, for any point in X, the preimages of any point in, so the preimage of any point in U is in one-to-one correspondence between elements of I, because for each U alphas here, there exists a unique preimage, because we know that P restricted to this guy arises a homomorphism. And okay, and this means that this UX belongs to equivalence class of X. This means equivalence class of this equivalence relation. Okay, so we know that of course the equivalence classes are non-intersecting, and they are open, because we show that any neighborhood, any point in the equivalence class has an open neighborhood. And so we have a cover of X by its equivalence classes, which are open, non-intersecting subspaces. And since we know that X is connected, there should be just unique equivalence class. So here I use the fact that X is connected. Questions?
Could you repeat the last argument?
Okay, so we know that so X is covered by equivalence classes. Equivalence classes can be used as subsets in X. And so we know that each of these guys is open. This is what is shown here, right? Because we show that for any neighborhood, we have for any element here in this subset, there exists an open neighborhood which belongs to X. And And we also know that all these the different equivalence classes, they do not intersect. I mean, if they intersect, then by definition they're the same. And we know that one of the definition of the space of being compact is that there is no if it's covered by a disjoint union of open subsets, this means that they are all empty but one, which is the whole space. Is it okay?
Please, I don't understand well the last argument. Why, if x prime belong in Ux, then x prime should be related to x?
Well, this comes. So the argument that if so for any x prime in Ux, the preimage of x prime is in one-to-one correspondence between elements of this I. So if I take Ux, I decompose it, so its preimage is a disjoint union of say Ux alphas, where index runs over some set I. And we know that so we know that they're disjoint, and for each, if I restrict P on each of these guys, for each alpha, it's homomorphic. It provides a homomorphism to Ux. This means for so any subset here, Ux alpha has a unique preimage of any point here, which is exactly this statement. And since they're both these preimages are in projection with I, and this by definition means that they're equivalent.
So in the definition of evenly covered, this I is uniform.
Well, this is what we prove. That it's I. Yeah, what we prove there is so for any if X is connected, so we show that for any I. Any i's are in projection with each other. For any choice of x or any choice of u, these i's should be isomorphic as sets. This is what we show. Any further questions? Of course, if it's disjoint, there can be multiple cars. For example, for S1, you take a disjoint union of S1, the cover can be something like this. There can be some, so this prism will cover it by kind of S1, which has three fibers, but over here, well, it has this three sheets each point, and here it has two sheets, something like this. Okay. My X joint union of two circles. here, of course, well, maybe I should give you a very basic. It's maybe obvious, but maybe I can give you a very basic example of the cover. So if you consider cover of a circle by itself. So again, we want to suppose we use a representation of a circle as Z mod R mod Z, and I consider covering map to be like this. Some, let's say, positive. Strictly positive integer, and so morally this means that this circle winds n times, like here 2 or 3 around the other circle. So in particular the induced map. So if I fix my base point here x0 to be just class of 0 and its lift, I can also class of 0. So P star is a map from Z to Z. So I guess this is one of the homeworks. So maybe I should go with this. So this sounds the one. So this covers. This is a. So this gives you a. Because this example is the subgroup. The image of phi star is a subgroup in Z, which is can be identified with multiples of n. I here okay. So now we want, the next proposition will be actually finding the algebraic meaning of this number, algebraic meaning of the number of sheets. So usually, if you want algebraic topology, studies relation between topology and algebra. So this is in the spirit of general spirit of algebraic topology. Okay, so again we consider some cover. Fix base point in x and its lift x0 tilde as usual. And let me assume that x tilde and x are path connected. And then the number of sheets equals to the index of following subgroup, which is the image of pi1 x tilde in inside y1. So from the last proposition, we learned that the image of pi star, the pi star is injective. So this image, yeah. In particular, this can be understood as a subgroup here. So in other words, this means that if we consider, so what is the index of H? One way to define the index is the number of cosets. Which is usually denoted like this. Is a set isomorphic to the image of, let's say, X0. I mean, from the remark before, we learned that I mean, this is the same up to bijection for any point, because X is path connected, and this is also the same as the number of the same as a set which enters in the decomposition of the preimage of evenly covered neighborhoods. And so the way we're going to prove this is by constructing explicitly bijection. And we'll do it this way. So consider a path on X starting and ending at 0. And take G tilde be its lift, such that, again, for the lift we fix the existing unique lift once we fix the starting point of the path. This can be unique, as we know. And also let me take some element in the subgroup H, which is the image of P star. It's represented by some loop, in X, and we know that from the previous proposition, so we know since it's in the image of P star, we know that it's unique, it's lifted to a loop, and it's based at X0. So again, if I took a general element here, it would lift to some path which starts at X0 tilde, but it may end at some other point. But since this guy is in the image, it satisfies it, its lift satisfies this condition. And then it follows if I consider the following composition of paths. H tilde, I go along H tilde and then I'll go along J tilde. This is so this is a well-defined. This gives me a well-defined composition such that it starts position of loop which starts at X0 tilde and ends so H tilde ends at x0 tilde, so then I have all divine composition. It ends at the same point where J tilde ended. Right? So the end point of this loop of path G tilde and the path obtained by this composition is the same. This follows that we, because of this equality, we can define the following map. So it will be a map from this set of left cosets to the preimage of x0, such that if I take a left coset like this, it is mapped to J tilde of 1. So we know that this thing, of course, so since G tilde was a lift of loop G, so we know that G tilde of 1 should be projected to x0. So this is definitely in the preimage of x tilde. It's a preimage of x0. And it is well defined exactly because of this property. So if I change G by if I multiply for any product of G element G in pi 1 and some element in subgroup H like this is mapped because of this condition. This is mapped to the same point.
Is it take H tilde in H or just H?
So I mean, the H represents a class in H, in big H. Well, H tilde is H tilde you can understand. Well, the H tilde is a loop in X tilde. I mean, the class of H tilde is element. You can understand the element of pi 1 of X tilde. But it's H itself is P star of this H tilde. this is remind you, the cosets are just subsets of the group. I mean, this is the definition of this G, H, the subset of a group of the following form. So left coset. And this map is defined by, so we take any element here, any element in the group in this coset, and we consider its lift at 1, the endpoint of the lifted path. And what we show that for any element in the coset, the image is the same, right? So all elements in the coset are mapped to the same guy here. So we want to show that this is a bijection actually, and so again one way to show it's this is both surjective and injective. So first let me show that this is surjective. X is path connected. Here, of course, I need classes. So yeah, X is path connected. This means that for any X tilde, suppose I take any point X tilde in the preimage of X0, that is the path, let's say, G tilde from X0 to X tilde.
Because the X0 is in X, but X0 should die is in X.
Oh yeah, okay, yes. From X0 tilde to X, and so one can take G to be a composition of this path, this projection P, and then from this construction we know that the sorry, this is not right now. The coset of a class of G equals to, well, so G tilde provides the lift of G. This equals to G tilde of 1, which is X tilde. Okay, so this means indeed phi is surjective. So for any element here, we found a preimage. So next we want to show that phi is injective. So suppose there are two cosets that two cosets which have the same image I want to show the same cosets. And okay, so by definition of this map phi, this means that so if I take the lift of G1 and the lift of G2, the endpoints are the same. This means if I can consider the following composition of lifts of lift of G1 and its inverse, an inverse of the lift of G2. So because this condition, this is well defined, and this will be it will be a loop based at x0 tilde. And it's so this loop provides the lift of following position of loops in the X, and so we know if so this is some loop. If a loop, we know that if a loop in X is lifted to a loop in X tilde, this means that it represents a class in the image of P star. This means that falls from the previous proposition, and so this is what we call H. But the other way, I mean, this we know that this is equivalent to taking this group operation in H, and this means that G1 is G2 times H for some H in some group H, right? And well, this exactly means that and this exactly means that the corresponding cosets are the same. And this means that phi is indeed injected.
In the definition of P, should it be necessarily surjective?
P,
The projection.
yes.
Then in the hypothesis, we just need that X tilde is path connected.
Yeah. Well, here we need to use that this is path connected. What is the question?
Because in the hypothesis, the two should be path connected.
Well, it's enough to have X tilde.
Yes, so it's continuous projection.
It's enough. I mean, if you have X tilde path connected, then X is is also postconnected.
Yeah, but we need the path, make it path connected because we need to talk about the number of sheets.
Yeah, but if we have P, then X is automatically path connected. If X is not path connected, then there is no P.
Well, let's see. I mean, there might be some weird situation when let's see, need X. Well, it depends. I mean, they want. And we have to be like, depends if we allow this I. I mean, maybe one can make a generic definition that I itself can be empty. Then P is not going to be not going to be surjective. I mean, it can be kind of empty. I mean, if you allow if you want to allow the number of sheets to be 0, then we actually want to require also X to be connected. So let us allow. So we want specify that X itself is connected. So this means. Because there might be a situation like S, I mean X is a joint union of S1, but here we have empty, and here we have some color. So this is plus connected, and this is not.
But it has to be surjective by definition.
No, not certain. No, we require that it's just P is we require just that the preimage, each point has a preimage which is the preimage of the neighborhood, which preimage is a disjoint union of sets homomorphic. So it can be, I mean, it can be an empty set. I mean, it depends how we want to define it, but let's define it so that it's.
Yeah, but if the data point in the second circle, the preimage has to be homomorphic to some neighborhood.
Well, it's the statement that the P1 if I take some U, P1 of U is a disjoint union of U alphas. Each of this. I mean, there is no contradiction. This is no direct condition. This is just there's no guys. It's just I is empty. So I mean usually for this generic definition, people want to assume that I can be empty. But again, I mean the case is like when X itself is not connected. I mean usually you just interesting happens. You just study its connected components independently. I mean, so usually, the non-trivial statements are made for when X is considered to be connected, and then this I is the same for any. Okay, I'll stop here.